Yes, we had so much fun with factoring in section 4. We're going to do another section, factoring some more. Let's factor sums, or differences of cubes. We know how to do differences of squares, don't we? That would be, for example, a square minus b square. And now, this is pretty exciting. A cubed plus b cubed, or a cubed minus b cubed. Factoring that seems like a fairly big deal. Factoring quadratic trinomials that have a leading coefficient of 1. All right, that's no big deal. We can always do those. X squared plus bx plus c. What's my leading coefficient? 1. Not hard for us. We've been doing that for a couple years now. Then, factoring quadratic trinomials that have a leading coefficient which is other than 1. Aha! This is the a x squared plus bx plus c, where my a is something which is not 1. Okay, so for a moment we're going to do a little review. We're going to try factoring this. The very first thing I look at is, see, I have wondering if I might have difference of squares here. Indeed. Difference of squares, it is. What is the square root of 25c squared? All right. With difference of squares, I know it is going to factor into conjugates. Square root of 16d squared? You can see I'm setting up my conjugates. They have the same first term. They have the same second term. The only difference between them, these conjugates, one is a sum, the other a difference. All right. Multiplying two binomials, we're going to FOIL this. We'll have x squared, that's our first, plus, what are we going to do next? Our outside, which is 4x, plus our inside, which is 3x, plus our last, which is 12. Combine like terms. And there we have it. A quadratic trinomial with a leading coefficient, yes, of 1. This is the same thing again. Let's do it. X squared, that's my first, plus my outside, which is 4x, plus my inside, which is plus a negative is a negative 5x, then plus my last, and my last is a negative 20. So at this point I regret having put that plus there, I want to go back and put a negative 20. Like terms combining, x squared minus x minus 20. That's our little review. More factoring. Now we're factoring sums or differences of two cubes. Here are the patterns that you should learn. Let's just take a look at them, see if there's some way we can help get these stuck in our minds. When we have a sum of cubes, one of the factors is the simple little binomial a plus b. So we have a plus cubes and we have plus the linear version here. Then we know this has to be x squared, because when we multiply these together we need to get back to cubed. We know this has to be b squared, because when we multiply the last and the last together we have to get this. And then we have again a middle term in this trinomial, but it's a simple middle term. I think I think it is a little easier than some we've seen. Why have we got a minus here? Well, we better have a minus somewhere, because what do we see? No middle term there, so we need a minus. We didn't have a minus here, so we've got it here. And we simply take the cube root times the cube root with a minus sign, and that's the middle of our quadratic trinomial factor. When we do the negative version of this, the difference of two cubes, our binomial has the negative. We only need one negative, so look at our trinomial, it's positive. So that's a little run through, hoping that that will help you remember how that is configured. Just for old time's sake, I have put in the difference of squares. You already are very familiar with this. This is factored into conjugates. Okay? Difference of cubes factors into a linear binomial and a quadratic trinomial. This one could be factored. You have to think of it then as either x squared and then cubed, or think of it as x cubed and then squared. We could try factoring both of these ways of thinking about it. This one, I'm thinking about it as a difference of squares. This way, I'm thinking of it as a difference of cubes. Where am I getting that? Difference of cubes. There's my difference. Or I could look at this as a difference of squares. Okay, so let's see how that would work. Working from a difference of cubes, what did we say we would have to do with that? We'd have a binomial and a quadratic trinomial. So our binomial would be x squared minus y squared. Notice what we're doing here. we're looking at this as a difference of cubes. And inside of this, we consider this to be our A and this to be our Y. Pretty tricky, huh? So this comes down, and this comes down. That's our binomial. And then we have a trinomial. We've taken our x squared and squared it. Then we say x squared times y squared with a plus. Then we take our y squared and square it. Looking okay, is it? Well, suppose we had decided to go this way. What's the difference here? Let me mark it. We're talking here of a difference of squares. So we look at this as two squares, one being subtracted from the other, and we consider in this version this to be our A and this to be our B. Let's see how that would go. Wouldn't that be true? Conjugates. Does that make sense? We have our A plus B and our A minus B, our conjugates. We're so familiar with this one. Whoops, I went backwards. And then we have two versions of a difference of cubes, which we are learning. The difference of cubes and the sum of cubes factor in a little bit different way, don't they? The sum, x plus y, the difference, x minus y for their binomials. The sum, x squared minus xy plus y squared. And the difference looks almost identical, except since it already has a negative over here, we have a positive here. All right. Let's go back up here now and think, how are these going to, they have to be the same, don't they? I love it. So this is a difference of squares, which is two conjugates, okay? This is like the most miraculous little puzzle. And over here, what's happening? We're taking this and we're going to try factoring by grouping. Isn't this clever? Factoring by grouping. So we divide the middle into two terms, or we re-express it, would be a better way to say it, as two terms which are equivalent to this middle term. And I'll show you why we do that. Now I can rearrange things a little bit. Oh, quite a little bit, right? I take this term and move it over here. So now this becomes a perfect square, trinomial. And this, of course, is a nice square. Aha, yes. And we know what we can do with this, right? Conjugates, right? Difference of squares can be factored into conjugates. And the conjugates look a little fancy, don't they? We take, this is our first term, here it is, and here it is. And this is our second term, here and here. One is a sum, the other is a difference. Woo! All right. Oh my goodness. Look at this. All I had to do now was kind of rearrange things. Put the y square over here and the y square over here, and it looks just like this. Once I've done that, you can see it now, can't you? These are matched right here, and these are matched right here and right here. So we can work either way to factor. Now, where did we have it factored the fullest? I don't know. I guess any one of these where we had the 4 factors were really good factors. Factoring sums or differences of 2 cubes. Sometimes you can use this to do some of the fancy mathematics in your mind. You can impress people with this. For example, this one. Does it fit this pattern at all? You bet it does. If you think of A as being 3 and B as being 5, we've got A minus B, so we're looking at this factor, or this pattern right here. A minus 5, A minus B, or 3 minus 5, and then this one is A squared, which is 9, yes, plus AB, which is 15, plus B squared, which certainly is 25. So we know that it could have been written as 3 cubed minus 5 cubed. So which is the fastest way to get to this? Well, this looks like a pretty fast way to figure out what 3 cubed minus 5 cubed is, because this would be my first parentheses. That's right, negative 2. And this, my second parentheses, if I add 15 and 25, I get 40 plus 9. So that would be a negative 98. Or I could look at it this way, which would be 27 minus 125, which also equals a negative 98. How about if I wanted to quickly figure out what this was using this pattern for the sum of 2 cubes? So this time I'm going to look at this one. That would tell me that for my first factor, I would have a plus b, that is 6 plus 4, that'd be 10. And for my second factor, I'm going to have a squared, which would be 36, minus 24. Am I right so far? Plus 16. So that's the same as 12 plus 16. So what is this all equal to? This would be 28, right? Am I doing my arithmetic right? Times 10. It's a little quicker than figuring this out, I think. Anyway, it's kind of fun. Factoring sums or differences of two cubes. So let's factor this. Just do it. Okay, I take the cube root of y cubed, which is y. And I take the cube root of 8, which is 2. And what's my factoring pattern for this? It's right here. So minus 2. Then it's going to be y squared. Remember, I only have one negative, so it's going to be positive. Plus 2y, right? I'm taking the cube root of this. Plus 2 squared. There we have it. Memorize this. It is very useful. This one you're going to use a lot. It's very helpful in standardized testing. Factoring trinomials of this type. Well, we know how to do that. What pairs of factors would you check in order to factor this one? Well, it would be 1 times 63. It would be, what factors make up 63? Well, it could be 9 times 7. And so I look at these and I say, if I add them together, 9 plus 7, will I equal 16? No. However, if I thought of this as negative 9 times negative 7, it still equals 63. And when I add a negative 9 to a negative 7, I get what I want. Okay, so let's try that over here. 1 times 45 gives me a target here to factor. 2 factors of 45. Let's see, it would be 9 and 5. And if I add those together, 9 plus 5, then I get a positive 14. So I know I've got x squared 9x. I'm going to split this 14x up into 9 plus 5. So 9x plus 5x plus 45. What I'm demonstrating here is factoring by grouping. So I'm going to group those two and those two. Look for a common factor in the first group. The only common factor I have is an x. X plus 9 when I factor out 1x. And then it's plus, let's see, 5 is common to both terms. I'll factor it out. And I have the good news I was hoping for, that now my first term, which is all of this, has a x plus 9 as a factor. And my second term has x plus 9, meaning that can be factored out. It's common to my first and my last. And after I factor it out, I'm left with x plus 5. Now, did that seem a long way around to do it? Actually, I kind of hope it did, because we are going to use this method was not actually needed here where we had a leading coefficient of 1, but we are going to use this method for more complicated ones. I want to show you that it works for the simpler one as well. Let's go back over here to our questions. These test whether or not we understand the concept. In this trinomial, if c were negative, would the factors have the same sign or opposite signs? Opposite, right? There's no way C can be positive if their factors are opposite. I should say that differently. There's no way that C can be this C can be negative unless they are opposite signs. If it's positive, they have the same sign. All right. Let's try this one now. We're going to use this factoring by grouping technique we've been practicing a little bit lately. So 8, we always take this leading coefficient, and then we take our constant, or whatever we find here, times a negative 15. This tells us what we're going to try factoring. Let's see. 2 times negative 15 is negative 30 times 4. So we've got a negative 120. Those of you with calculators can verify that. Now, how could we factor 120, negative 120, so that when we add the factors together, so if I said negative 12 and a positive 10, when I add those together, negative 12 plus 10, I get exactly what I wanted. So now I know what I'm going to do with this middle term. The first term remains untouched. The third term remains untouched. The only thing I'm going to alter is right here. Instead of saying negative 2x, I'm going to say negative 12 plus 10x. Now I have set it up to do factoring by grouping. I can factor out an x, and there's more I can factor out, isn't there? I can factor out a 4. When I factor that out of this, the first 2, what gets left behind? That's right, 2x minus 3. Over here, plus, and now I'm going to look at these two. What can I factor out of here? Yes, a 5, definitely. 2x minus 3. I don't know about you, but I am always very happy when this pleasant result comes up, where I have in my first term a factor, it's a binomial, that is exactly the same as a factor in my second term, meaning I can factor it out. You can only factor something out if it exists in both terms. When I divide each by 2x minus 3, I'm left with 4x plus 5. Now, isn't that a wonderfully easy way, systematic way, rather than the old guess and check? I love it. And I think we've been through this, or something so like it. We're not going to go with it. See you in class.